Hey again. It's time for mini lessons. So if you turn to the part in your papers that looks a little something like this, we can talk about how to build off of the ideas that you guys did an amazing job thinking about 2 days ago in class about what dissolves in water and why it dissolves in water. Today's purpose is to sort of start describing how much can dissolve in water. So even something that is very easily soluble in water, like table salt, you can't just dump as much table salt as you want into a beaker of water and expect it all to dissolve. There is a limit, and the limit is what we're going to be talking about today. We're going to be putting some numbers to that, and of course, with numbers comes reference tables. So you're going to be using reference table G today. So if you don't have your reference tables out, pause the video right quick and get them out, turn to table G, take a look at them. You're going to be using that today during workshop. So this graph shown here is not something that's off of table G. This is the solubility curve of sugar. And what it tells us is how many grams of sugar can dissolve in 100 grams of water at various temperatures. And as you notice, the solubility seems to increase with increasing temperature. That makes sense. If you want to dissolve more stuff, like more sugar in coffee or something, you want to try and make it hotter. You guys know this from experience. This is just putting some data points that tell us exactly how much sugar can, air quotes, fit into a certain amount of water, in this case 100 grams. Chemistry has some vocabulary that goes along with this idea of how much can fit. And the first term is saturated, which, yes, you may remember from organic chemistry. A saturated hydrocarbon was filled with hydrogens. You couldn't take any away. They were all surrounding the carbons. In the case of solubility, saturated means as full as the solution can be with solute. And remember, solute is the stuff you dissolve. So it's typically like a solid. You're going to be looking at a couple cases in which it will be a gas, but it's the stuff you're trying to cram into the solution. And that line on the graph shows us where something is saturated. So that line is the limit. And what gets kind of interesting, and you guys are going to work with us a little bit during workshop, is that when we start adding stuff into water and dissolving it, it changes the properties of the water. It's no longer a pure substance anymore. It's now a mixture, and mixtures have different properties. So in the case of creating solutions, whether they're saturated or not, we're actually going to get something a little bit different. So I'm going to slide this down a little bit and try and draw myself a beaker of just pure water. And you guys know that some of these water molecules have the potential to escape as gas, and that's what we call vapor pressure. And some of these water molecules might sort of come together and form ice, and that would be freezing or solidification. That process happens fairly easily for water. We've got to deal with the hydrogen bonds, yes, but there's no other molecules in the way. When we start dissolving stuff, especially when we dissolve as much as we possibly can into water, what we see, I'll draw a second beaker over here so you can have a means for comparison. What we see is that the stuff we dissolve starts getting in the way of the changes that the water wants to make. So instead of having just pure water, now we've got all this junk sitting in between water molecules all over the place. We can have a little junk or a lot of junk, but if we're saturated, we've got as much junk in there as possible. Now, you guys are going to be thinking about how that affects boiling point and freezing point, but just to sort of give you a preview of that thought process, imagine your water molecule here trying to get out and escape as gas. So you're trying to boil. If you're over here, you've got a nice clear shot straight out. But on this side, you've got a whole bunch of these solute particles kind of blocking your way. This is like if you're going to the bathroom in the middle of class and it's like the hallways are pretty clear, it's a pretty straight shot. Over here, it's during passing time and there are literally 10,000 people in your way and you can't move anywhere fast at all. So you're going to have to add a lot more energy to this particular system if you're a water molecule that wants to escape. So we're going to affect the amount of energy, increase the amount of energy to boil. So instead of boiling at 100 degrees, we might need to crank the temp up to 105, 110. It all depends on how much stuff is dissolved in that water. Consequently, the opposite is also kind of true. If you're now a water molecule that's trying to freeze, you want to huddle closer to your other water molecule friends. Over here, it's nice and easy. You just zoom a little closer, take advantage of the strength of the hydrogen bonds that connect you guys, and freeze yourself. Order your particles so that they're nice and geometrically structured. Over here, if you're this water molecule trying to hook up with your friend right here, you got this junk in the way again. So it's harder to get the water particles closer so that they can form the solids that they want to form. So we have to take out even more energy if we want it to form a perfect solid. So just like we had to add more energy to boil, we have to take away more energy to freeze. Because remember, freezing, you got to get the energy out. So we got to get extra energy out. So take out more energy to freeze. So the end result there is that if this is our pure substance, adding this solute and especially making a saturated solution is going to create a scenario where your boiling point goes way up and your freezing point goes way down. And we're going to be talking about this a little more, not just in this class, but also next class when we talk about concentration. But you're going to start getting the conceptual ideas today during workshop as you go. So there are 2 more vocab words that we got to cover before you guys run loose on workshop. And those 2 are related to this idea of being full. If you're unsaturated, it's like being unsatisfied. You must not be full. So unsaturated, when we talk about solubility, means more solute could be dissolved. So you're not full. And on the graph, as you can imagine, if that line represents what it takes to be full, what it takes to be saturated, I'll highlight in the area where we are unsaturated, and that's going to be this whole mess down here. So let's say it's 80 degrees and you've got 100 grams of water and I throw in 200 grams of sucrose, 200 grams of sugar. I fall in this region down here, which tells me I could still add another 50, 100, 150-ish grams of sugar until I'm completely full. So if I've only added 200 grams, I am unsaturated. I've got a ways to go before I get up to that full line. As you can imagine then, supersaturated, that other word down here, means that too much solute has been added. Now, solutions do have a limit, right? When they're saturated, they're completely full. If you're supersaturated, that means you're completely full, and then you kept trying to add stuff in. And that extra stuff isn't going to dissolve. It's just going to sink right down to the bottom. You guys have seen this before if you tried to add too much of any of those solid contaminants to your test tubes in lab the other day. So on that graph, anything that falls above your saturated line is going to be classified as supersaturated. So anything up here. So again, if we're at 80 degrees and I've added 450 grams of sugar, I need to know that there's going to be an extra about 100 grams in there. So I'm going to have an extra 100 grams of sugar just sitting on the bottom of my beaker. All right, so use workshop as a chance to work with these vocabulary terms. See what you can do. When you have struggles, call Ms. Polton over. She's here to help. And if you have any extra questions, I'm going to be around at the end of the day today in homeroom and after school. So do your best. Good luck. Do it to it.